One way that we make decisions from data is with confidence intervals. In class, we'll look at the formulas and how to actually build them, but before we do that, let's look at some definitions and notation. Statistical inference very often includes using a sample to infer characteristics of the population. Besides measuring characteristics of the sample, we also need to provide a measure of how confident we are in our sample and therefore in our conclusions. Here's a very simple example of what we're going to be talking about in this section. Let's suppose that I grade a bunch of exams for a class, and then I take the average of all the exams, and that means I know with certainty the population mean, the population exam average on the test. What if I forget the number, but I remember it was somewhere in the 80s? So I might say the average is somewhere between 80 and 90. That's an interval, a guess that includes the true population average. Or maybe I remember that the average was in the 80s, but was a B plus or close to a B plus, so maybe I say the average is somewhere between 85 and 89. This is another guess that includes the true value, but a narrower interval, a narrower range, because I remembered more information. So what if I didn't have time to grade all the tests? What if I decide to pull out a random sample of tests from the class and I only grade those tests and I compute an average for the sample? Will the average for the sample mean match exactly the mean for the entire class? Maybe, but probably not. And because it's a random sample and because I know something about probability, I can use probability to measure the certainty of my sample mean. So when I have a random sample, I'm going to build an interval around my sample mean, and I'm going to use probability to give a measure of certainty. So here's our first definition. A critical value is a number that separates statistics that are likely to occur from those that are unlikely to occur. We're going to start out talking about the normal distribution, so in this video, our critical values will be z-scores. The confidence level is the proportion of times that the confidence interval actually does contain the population parameter, assuming that the estimation process is repeated many times. In this class, the population parameter could be either a population mean or a population proportion. Previously in the class, we've assumed that the 95% in the center is usual and the 5% in the tails is unusual. Starting now with this chapter, we get to decide, or the textbook author decides for us, what percentage or proportion we want to be usual and unusual. You might remember from chapter 7 that the Greek letter alpha stands for area, and we use alpha to measure the area in the tails. So the notation for the confidence interval is 1 minus alpha times 100%. What does this mean? Let's say that we want 95% to be considered usual. So then 5% is in the tails. So alpha is 0.05 and 1 minus alpha is 0.95. Therefore, we have a 95% confidence interval. Let's look at some different confidence levels and what that means. In this graph, we can see the true population mean marked as mu. If we have a confidence level of 70%, that means that the interval we build around the sample mean will contain the true population mean 70% of the time if we repeat the sampling and estimation process many times. A confidence level of 95% gives us a wider interval, because now our interval will include the true population mean 95% of the time. If the confidence level is 99.7%, then the intervals are even wider because our interval will include the true population mean 99.7% of the time. Keep in mind that we don't know the true population mean. We are taking samples so that we can estimate the true population mean. All we can know is the proportion of times based on probability that our interval will contain the truth. Also keep in mind that this particular illustration shows the population mean, but we could also be talking about the population proportion instead of the mean. Let's review from Chapter 7. Recall that Z stands for the standard normal distribution. The number Z with a subscript of alpha represents the Z-score that separates an area of alpha in the right tail of a standard normal distribution. So if alpha equals 0.05, that means we have 0.95 of the graph, or 95% of the graph to the left, and a proportion of 0.05, or 5%, on the right. So I can use the inverse normal function on my calculator to find the z-score, which turns out to be 1.645, meaning that a z-score of 1.645 separates the bottom 95% of the z-scores from the top 5%. What if we want 95% of the curve in the center? That gives us 2.5% in each tail. And when I use the inverse normal calculator function for 0.025, I get a negative 1.96. Because this curve is symmetric, the two z-scores that separate the center 95% are negative 1.96 and positive 1.96. You will see notation in the book labeling the critical values as positive and negative z with a subscript of alpha divided by 2. The number z, subscript alpha divided by 2, is the critical value for the right side of the standard normal distribution. The number negative z subscript alpha divided by 2 is the critical value for the left side of the standard normal distribution. Let's look at what this means. If I have a confidence level of 95%, that means I have an alpha, the area in the tails, of 5% or 0.05. To find the values of positive and negative 1.96, I took the value of alpha and divided it by 2, and I used the area of 0.025 to find the critical value. Don't look at the notation and think that you should take 1.96 and divide that by 2. Please don't do that. We divide alpha by 2, not the critical value. Sometimes you will also see the critical values marked as ZCV and negative ZCV. Once we have a critical value, we can use that to build a margin of error. The margin of error is the critical value times the standard error of the statistic. Remember that the standard error of the statistic is another name for the standard deviation of the sample statistic. And the critical value tells us how many standard deviations we need to be from the mean to find values that are unusual or unlikely. So when we multiply the critical value by the value for the standard deviation, we know how far we need to be from the mean to include the values that are likely to happen. Once we have the margin of error, then we will add and subtract that from our point estimate. If we are using a sample proportion to estimate a population proportion, then the point estimate is the sample proportion. If we are using a sample mean to estimate a population mean, then the point estimate is the sample mean. I realize right now I'm being very vague about these formulas, but we will go over the formulas in class. What I want us to think about right now is what goes into this margin of error, this measure of how confident we are in our estimate of the sample. The margin of error depends on 3 factors. As the level of confidence increases, the margin of error also increases. Let's look at this illustration again. If we want to increase the proportion of times our interval hits the true value, then the margin of error increases. If we decrease the confidence level, then the margin of error also decreases. As the sample size increases, the margin of error decreases. More information in the sample gives us a smaller standard error for the sample statistic, and therefore the margin of error is also smaller. The bigger the population standard deviation, the more spread there is in the population, the more uncertainty we have in the population, so the margin of error will be bigger when the population standard deviation is bigger. Again, we will talk more about the formulas in class, and we'll see exactly how to build a confidence interval.